This is Suvarchala, working as an associate professor, Department of Computer Science and Engineering, Institute of Aeronautical Engineering. So, part of the design and analysis of algorithm lecture series. In this video, would like to explain about tree traversal techniques, and also what is the difference between recursive and non-recursive tree traversal techniques, and also the time and space complexities of these two kinds of techniques actually. So we'll define basically, of course, all these terminology, we aware of this terminology based upon the data structures concepts. So just we will revise briefly about what is tree, binary tree, and what are the traversal techniques, tree traversal techniques, recursive algorithms as well as non-recursive algorithms with examples we'll discuss. Then we will analyze the traversal techniques. So a tree comes under the non-linear data structure, one of the non-linear data structures. The set of elements that either it is an empty or it has a distinguished element known as a root and 0 or more trees further. We will call them as generally subtrees of the root actually. So this can be defined, considered as a, what kind of this definition means here? What this definition is considered to be as a recursive definition. If you observe that it is empty or it has a distinguished elements called root and 0 or more trees, again it definition consists of tree word again. That means it's a recursive. So that's why what is the base case and what is the recursive part must be analyzed by us, so that what happens, the base case satisfaction can be considered by us in general definition actually. So recursive part is there. If you observe here, root, red color is root. It is having various trees. This is the first one, second one, third one, fourth one. Right? Root is having 4 trees again. So subtrees we are going to come. Each of them again is having a root and subtrees are there. In this example specifically, that is the definition of tree is a recursive process. This process is continued till each node array will be considered as doesn't have any further subtrees. So that's why the tree is going to be defined as in terms of recursive definition. Generally, we will call these trees are a general tree. If we didn't add any word also, we will consider it as a general tree, which consists of multiple children. That means a tree, each of whose nodes may have any number of children, we will call it as a n-array tree, or in terms of general tree, we will call it as. But if there is a restriction, a tree, each of which nodes may have not more than n elements or n children, then we will call the respective tree as a n-array tree. So, the management of general tree is a little bit tedious task, because each node we may not expect how many children will be there for each node at each node. How to manage those nodes for various operations will be a little bit tedious task. So generally, while using these trees for real-time applications in any application, we will consider n-array trees only. A tree each of which whose nodes are may be having not more than n means we may manage our traversal or memory management of the node can be considered up to maximum n subtrees it may have. Most popular of these n-array trees is binary tree, that is 2-array tree, that is we will call it as a binary tree. So based upon the previous definition, a tree each of whose nodes may have not more than 2 children, because n value is here 2. So not more than 2 children, we will call the tree as a binary tree. That means each node of tree will have at the most 2 children. So that's why 2 children means degrees arity of our tree is 2 actually. So the children, if present, 2 are present also, we will call them as a left child and right child, because only maximum 2 children. So these children can be distinguished as a left child and right child in terminology. So as in case of tree we defined recursively, here also A recursive definition of binary tree can be considered as it is an empty tree or a tree which has a root whose left and right subtrees are again binary trees. So here we have a specific value for our subtrees, no? So that's why whose children are going to be left and right subtrees are again binary trees. We will call it as a binary tree. So a binary tree is also known as a positional tree. That is, it matters whether the subtree is either left or right. So that's why we will always first child left side child will be first one, leftmost one we will consider it as a left child, and the next one, second one, we will consider as a right child. That is positional wise we will always see use the words definitions as well as the respective positional way we will use the accessing of the subtrees actually. So that's why left subtree, right subtree we will consider. For example, here if you observe here, this is a tree. So 2 is having 2 children. So 2 is a root here. 2 is having 2 children. That is left subtree and right subtree. Again, left subtree parent is 7. No? So that is considered as 7 is a root again. Again, it is having left subtree and right subtree. 5 is a root again. It is having only one child because left child is not there. Only right child. So right subtree is available this. So that's why we are going to call, if you observe here in this tree, each node will have maximum of 2 children. Maximum of 2 children means it may have 0, 1 or 2 children. So that's why this is a binary tree. Representation of such binary tree in memory or implementation of such binary tree is a little bit easy comparing with our general trees or other NRA trees. So various operations we can perform with our binary tree. For example, the basic operations with any data structures are going to be traversal, adding an element, deleting an element, sorting elements, searching for an element. These are the 5 operations, among which all the remaining operations are based upon our traversal techniques. So if you understand these traversal techniques properly, the remaining operations can be easily understood by us. So unlike linear data structures, arrays, linked lists, queues, stacks, etc., the traversal of these non-linear data structures, trees, will have various techniques or various methods. So linear means only sequential, no? So in only one order only the data will, we have to traverse. The elements are going to be accessed through traversal by traversing in one direction only, linear way. But non-linear means it may traverse in any way actually. So that's why all non-linear data structures will have various techniques to traversal of the respective data structure. Similarly, tree also. Traversal means what is traversal? Traversal is accessing each element of the data structure at least once. It's once only, not at least. It has to be accessed only once. Then we will call it as a traversal. That means each node of our tree must be accessed once. Then we will call it as a traversal process. Various ways we can traverse, no, actually, because the order here it is not a sequential, so various order of elements can be outputted by the different methods of traversal techniques. So the following are the generally used ways of traversing trees actually. We will use pre-order, in-order, post-order. Of course, one more order can also be considered by us. Level order is also there. But popularly or the commonly used tree traversal techniques are pre-order, post-order and in-order techniques. So we can distinguish our nodes of a tree like the root, left subtree and right subtree. These are the 3 words we are going to use or terms we are going to use while doing this traversal, because the tree consists of left subtree and right subtree. In case of pre-order traversal, if you observe this based upon, for example, we are going to have left subtree, right subtree is there. If left subtree and right subtree is there, depending on the position of the root node, we will call it as a root node as a represented by, let us assume that n is the root node. Because if you are going to use R again, R and right subtree may get confused. That's why let the root is going to be n. Let us assume that. Or you can use the word root. Depending upon the position of this root in this left and right subtrees order, the respective traversal technique is considered. Pre-order traversal. Pre means the node is going to be traversed before your left subtree and right subtree. That is, the root is going to be traversed first, visits first. Then its left subtree, then its right subtree. Again in the left subtree also, the root is going to be first traversed. Again, then it will move to the left subtree and right subtree. So pre indicates that the root is going to be traversed first before the left and right subtree traversals. Next, second traversal technique is in-order traversal. In order means in. So, the root position is placed in between L and R. That is, left subtree is traversed first, then node will be processed, then right subtree is going to be traversal. That means at each node, first left subtree is going to be processed, then the root is going to be processed, then right is going to be processed. That means the node or a root position is in between L and R, so that's why it's in order. Post order, post means after. So that's why left subtree is first traversed, then right subtree will be traversed, then the root is going to be get processed. So based upon the position of the root in the left subtree, right subtree order, the various three types of traversal techniques are going to be considered. So if you observe here, pre-order traversal visits the root first, traverse the left subtree, then traverse the right subtree. In-order traversal technique, traverse the left subtree first, then traverse the root, visits the root, then right subtree. In post-order, traverse the left subtree, then second one traverse the right subtree, then visit the root actually. So these are the three traversal techniques are there. So how these three traversal techniques are going to be considered for an application, we will see through some examples. We will consider in-order traversal. For each of these traversal techniques, we can write algorithms, programs or pseudo code by using two techniques: recursive procedures and non-recursive procedures. Recursive procedures means the traversal in your traversal algorithm or traversal procedure, traversal program itself, it is going to be called. So, if it is a recursive algorithms, as we are aware of that, it will use a stack internally, and the stack operations are going to be performed by the respective recursion process. So, non-recursive means internal stack is not going to be used, but we will use our non-recursive process of our traversal techniques are going to be explained by using additional auxiliary memory space also. So using recursion, the function will call itself left subtree, then print the current value and then calls itself on the right subtree. The result is that it prints the tree values in a in-order traversal. That means in-order means left root right. So root is in between left subtree and right subtree. Where is this in-order is going to be used? If you are going to consider this binary search trees, the in-order traversal nodes will give us in a ascending order of the data, if it is a binary search tree. Or if we are using our binary tree to represent our arithmetic expression, in-order traversal of that particular arithmetic expression results in the infix form actually. So various applications are there, or various needs are there for in-order traversal techniques. So the normal algorithm is, let us assume that it is a recursive procedure. First we will consider in order, 3 pointers will be there. Tree pointer is PTR. PTR is our root it points to. So each node is represented by 3 parts. Value will be there, left subtree address and right subtree address. If it doesn't contain left subtree, it will be null. Similarly, if it doesn't contain right subtree, it will be null. Like that we can implement by using linked list notations. So what is INORDER? If you are going to consider INORDER means if it is PTR is not equal to null, then only traversal is continued. If PTR is equal to null means the root is going to be, or the node itself is going to be null, it means that it is empty. So if it is empty, we have to stop. So this is the checking of emptiness, empty tree, or there are no further subtrees are existing for this node. So if PTR is not equal to null only, we have to process. If PTR is equal to null, we can stop. Because no elements are there in our root, we can stop. So you observe here, INORDER, we are recursive procedure. Now first we have to process left subtree, then we have to traverse left subtree, we have to process the node, then we have to process right subtree. So traversal of left subtree, traversal of right subtree means again in the same of INORDER. So that's why we are using this recursive process. INORDER of PTR left child. PTR left child means it gives the current node's left child address. After that, this is the first. Second one, we have considered LNR. So left is recursive procedure called because it's being a subtree. Then node means root. Root can be processed. Visit can be anything, either printing or counting elements, whatever it may be. So we are accessing now. We are visiting it. Then third order is right subtree processing. So right subtree processing again, we are using our recursive call in order of PT. This is left child processing. This is right child processing. In between, the node is going to be get visited actually. Right? So, INORDER traversal can be considered for such purpose actually. So, how it works, we will see with an example. INORDER left root, we are going to consider right. So, first left subtree means we have to move to the left side. Now, 4 is our left subtree root. Further, we have to, in that also left subtree 2, but it is not further processing. So, 2 is going to be displayed. 2 is the last one. There is no left subtree. It will be visited. Then it will be root itself. So root is visited. Then it will move to the parent. Parent is 4. Already left subtree processing completed. So 4 is going to be visited. So that is, then it will come to the right subtree. For right subtree also, it will check whether there exists any left subtree or not. No. So that's why root is going to be processed. The 6 is going to be processed. Then afterwards, it will move to the again to the root. Because this complete left processing is completed. So how it works? First it will move here. Then from here, it will process here. Then it will come to the right subtree. So INORDER means first it will process the left node only, which doesn't have any left. Then we will process 8 because node root is there. Node is means root here. Then we will move to the right. Right side again subtree is there. 10 is the root. But root is not going to be processed. It will move to the left child. 9. For 9, there is no further left child. So 9 root is going to be processed. Then it will move to the root again. Root of the subtree. That is 10. Then we will move to the right subtree. In case of right subtree also, no children are there. So the root is going to be processed. So the INORDER traversal of this tree is 2, 4, 6, 8, 9, 10, 11. We consider it a binary search tree, no? So that's why we are getting here ascending order of the data. So what is binary search tree? At each node, the elements of its node, left children are going to be having the lesser value of the root node and all its right subtree values are greater than that particular node actually. So if the duplicates are available, either of the side, either left side or right side, equality can be added. So we'll consider the next traversal techniques, preorder traversal technique. Again, using recursion, we will do this process. This preorder traversal technique is used to get the prefix expression of any expression. As INORDER is for infix, preorder can be used if you represent our arithmetic expressions by using a binary tree. Then pre-order traversal gives prefix form of the arithmetic expression. So the result of we will consider here as again, the visiting means printing only. The result is the printing of the tree values in pre-order actually. So how pre-order, what is pre-order? Root, left, right. First root has to be processed, then it move to the left subtree. In the left subtree again root, left. This process is continued. Once the no left subtree exists, then it will move to the right subtree and so on and so forth. So if you consider a small recursive algorithm, pre-order means first process the root no, so visit t or print t, whatever it may be, would like to use. Then left subtree must be traversed, then right subtree must be traversed. Again in the pre-order no, so that's why we are using recursive process of left subtree and right subtree. So we will use this recursive process of left subtree and right subtree so that the traversal can be in pre-order actually. How it works, we'll take an example here. Pre-order means root, left, right. So first root has to be processed. So 8 is going to be processed first. Then it will move to the 4. So 4 is going to be processed because it is moving to the left subtree. In the left subtree also again root. What is the root value here? 4. 4 will be processed. Then again it will move to the left subtree. 2 is the root. Root will be processed. No left subtree. It will come back to the again root. From the root already root processed no. So it will move to the right subtree. For right subtree also no further left or right. Left subtree is not there. So root is processed first. No left, no right. So it will move to the next, its parent again. So 8 is already processed. We will move to the right subtree. In case of right subtree, what is the root of the right subtree? 10. So 10 is going to be printed first. Then it will move to the left subtree. In the left subtree, 9 is there. Further, no children. The root itself is processed. No children are there. It will go back again. So for 10 again, it will take the right subtree. Right subtree is having a root as 11. And it will be processed. So the order in which we are getting 8, 4, 2, 6, 10, 9, 11, which is going to be in a pre-order. So similarly, we'll consider the post-order. Post-order, again, recursion by using this subtree can be called. Each subtree must be again processed in the post-order only, no? So the recursive procedure can be used. So left, right, post means after that root. So first left must be processed, then right must be processed, then it has to be processed root. So one of the applications or one of the uses of this post-order traversal of the tree is printing of the arithmetic expression in the form of postfix if you represent our arithmetic expression as in the form of a binary tree. So how the post-order traversal works as a small recursive procedure here. So post means after left, first left subtree, then right subtree. Again, these two are in a post order only. So recursion must be applicable here. Post order traversal of left child and post order traversal of right child. Then this node is going to be processed. This is going to be recursively processed by us. So post order traversal means here post order of left right root we are getting here. So left means it will start from 8, left means 4, again it has in left 2 and there is no left for the 2. So to process, again there is no right also. So left, no right. Then root will be processed. Root is 2 now. So 2 is going to be printed. After that it will go back to the parent. So already left is processed. For 4, 2 is the left and 6 is the right. So it will first move to the right subtree. For 6, no left and right. So root is processed as 6. Then it will go back to the parent. Now parent is going to be printed. That is root is going to be, root of the left subtree is 4. So the order is 2, 6, 4. Similarly after that we are moving to the root. But what is the next order? Left subtree completed means right subtree must be considered by us. In the right subtree again 10 is going to be root. Its left child is 9. 9 will be processed. Then its right child is 11. 11 will be processed. Then the root 10 will be processed. Finally 8, the root of the main tree will be processed. So what is the order of our post order? 2, 6, 4, 9, 11, 10, 8 is at the post order techniques. Of course, one more order is there. We will call it as a level by level order. Level by level means first root, then the next level elements, etc. We are going to consider. Each node is pointer and puts its children on the FIFO. That is a queue. First in, first out queue structure. When the FIFO is empty, then pointer is going to be null. Otherwise, delete a node from the FIFO queue and call it PTR. This is a small level by level order. We will use this level order technique in graph traversal techniques actually. So this is an exercise. Please traverse, write in order, pre-order and post-order traversal of the following trees, which makes you comfortable with writing or traversing a tree in order, pre-order or post-order. Now our primary objective is these three traversal techniques we explained by using a recursive procedure. If you observe recursive procedure, it is a lot of logic is there actually. But because of recursion, the length of the code was reduced as well as the logic of the code is also not that much considerable in writing because only 3 lines program we have written. So implementation is also, it takes physically, it is less number of steps only. But when we are using recursion, each recursive call is pushed into the stack, and when the recursion reaches or meets our base condition, from there onwards it pops and executes based upon the base condition results actually. So that's why it will take more time internally, and it uses stack operations, pushing, popping and stack operations also if it is recursion internally. If we don't want to use our recursion process, a non-recursive process or iterative process is needed for our tree traversal techniques. This is the pseudocode. Here also we are using stack. In the recursive process, internally system uses. We need not worry about the management of the stack operations. But here we are using explicitly by ourselves. We are creating a stack, and first we will push. It is a in order traversal. No, in order means we have to first traverse left one, then we have to traverse root, then right. So this is the way we are going to follow. Push the root into the stack. It will be set, then root is equal to root dot left. That means we are continuing to the left side, left subtree. This process is continued till it hits a null value. It hits a null means no further left children are there. Then it start popping and checking whether right exists or not. If right exists, what you supposed to do? Otherwise, it will be processed. So, if root is null and stack is empty, then we will return completed the traversal. So, stack is also empty or not, we have to check. If stack is non-empty means further nodes need to be processed further actually. So, that's why otherwise, pop the top node from the stack and set it as a root and print the root because left subtree completed, no root is going to be printed. Then again we will do the same process for right subtree. So right is equal to root is equal to root dot right and move to the step 2. Step 2 means again root is pushed. Again from there onwards leftmost is processed. So by using this pseudo code, we can implement our non-recursive procedure or approach of in-order traversal also. So this is a pseudo code. Just like English we have written, but a little bit, program-based implementation we will consider here. We will write an algorithm, in-order algorithm, C notation or the notation which we discussed at the earlier initial videos of this course. We discussed some notations, that notation we are using. So in-order traversal, stack we are first initializing as 0. Vertex is equal to root we are considering, while vertex is not equal to null, and we are doing this process pushing, and vertex is updated as a left son of vertex. We can use either PTR, we can use vertex, anything you can use. That means just we are traversing till the leftmost part. Once it is reached leftmost, then we will try to print and move to the right children of the at each node also. Pop the element from the stack and make it as a vertex. While vertex is not equal to 0, print the vertex first, then update the vertex with the right vertex. Then we'll move to the again top. Top is a position from where again it has to be repeated by. So by using these two techniques, either both are one and the same. Pseudo, if it is algorithm, directly you can convert into any programming language to implement it actually. So that's why we are going to use this. We will take an example and we will check how this non-recursive procedure works actually. Let us assume that this is the given tree, and normally we will write by using our previous techniques. In our pre-order traversal means first node has to be processed, then left. So that's why A, then we will have B because node B, and third one is D. So after node left one means G, then K, no right for G. So that's why it will remove. Then for D there is a right, H will be processed. After K, H, then left is L, then again right is M. So this is 1, 2, 3, 4, 5, 6, 7, 8. Again right subtree we came. Again here also first C9 is the 10. This is the pre-order traversal. Before left and right subtrees, the root is going to be processed. Similarly, this is the post-order, and this is pre-order, and this is in-order traversal techniques. So post-order means the root is going to be processed after the leftmost child. So if we will process till leftmost and there is no left children, so the first processing will be done by its leftmost child as a K. Then it will process its right. So no left, no right, so root is processed. Then we will move to the upward parent. So left child is processed, then right child. For G, no right child. So G is processed, root. Again we'll move to the upward. After K, G, D is the root. Left child completed, left subtree. So right subtree again, L, H, M is there. Again we will move to the leftmost one. So this will be the 3, right will be the 4, and the node will be the 5. That means K, G, D and L, M, H. So then we will move to the upward direction. B, left child is completed, no right child. So then B is going to be processed. This is 6. Left subtree of A completed, and we will consider right subtree of A. Then only we will move to the root again. So for this right subtree of A again, we will move to the leftmost one. So first left, no right here. So then root. E, C will be there. After left completed, right completed, then the root, 9th one is the root actually. This is the post order. So pre-order is completed, post order is completed. Similarly in order. Leftmost first root. So then right. Then we will get this is 1, this is 2, no right. Again 3 root, right is this one. In this also again 4, 5, 6. Then we will have here 7, no right. So 8, again left 9, root 10. That means you are going to have here K, G, D and L, H, M, then B, then A, then E, C. So like that we can get these the 3 orders of the table traversal. We will check by using non-recursive procedures whether we are getting it or not with the non-recursive procedures of the traversal techniques. So in order, already I explained you what the algorithm as a pseudo code which has been given here in the left side, and we will check one by one the each step of this pseudo code based upon which the tracing was given to us. So what are the things we have to always trace? Current vertex, which vertex we are processing, what is the position of the stack, and what are the nodes are processed. Processed means printed directly. And we will use the operations, what are the operations we are performing. So create a stack with 0 elements. So first one, this is the first one, and push the root into the stack. So we are, first element is going to be considered as 0, and this process is continued. The stack is empty means stack reaches 0th position. So we are push the root into the stack and set the root as a left of root. This process is continued A, B, D, E, K up to K. That means we are pushing and updating our root. Root will become first A, then B, then D, then G, then K. left of this. Every time we are pushing. And we reach null point. There are no children for k further. So, till this push the root into the stack and set root left continue till hits null. We reached null. Left of k is null. We will stop there. If the root is null and stack is empty, so if the root is null and stack is empty, then we can stop. But the stack is not empty. Stack is having some elements up to k elements are there. So that's why we will continue to the else part. What is else part? Pop out from the node. So we popped. So after popping k, we are processing that. We are printing. And what is the status of stack? Then 0, A, B, D, G only. And we pop the node, print and set the root as a write of root. So what is the root now? K is the null value was written. Print the root and get write root as a root of write. We printed root is now k. So we printed it and so write of k means no write of k. So we are go to step means step 2 we move. We are pushing again actually. Push the root into the stack and set the root as a continue till the root is. But root left of root is again null. So it won't do anything and it will come out. Then it will execute the else part because the stack is not empty and it will pop the next element. Pop the next element G. G is printed here and it will update our G, write of G. No write of G. Again it will pop out from D and update our root as a write of D. So what is write of D? So write of D is a H. So this is going to be executed now. So H is pushed into our stack. So after D, H is pushed into our stack. Then L is pushed into stack and left child of L is null. It will come out of that particular loop of the second step. Still stack is non-empty. So else part will be get executed. L will be popped. It will be printed. No right child for L. So the next one is popped. H will be popped and it will be printed. For H, yes, right child is there. M is the right child and M is updated. M is pushed into my stack and left of M is null. It will stop. Again, it will come here. Still stack is non-empty and it will pop out the M and M is printed. Right of M is null. So it will be continued further. Then it will be popped to the next element. That is after popping M, AB is then B will be popped out and B doesn't have any right child. B is printed. B doesn't have any right child. So the stack is not going to be added any further elements. Then what it happens? A and A is popped out. Now stack is empty but A is there. No. So right of A means the right of A is constituted as a C here. After printing A, we are going to get C is right of A. Left of C is A pushed into stack. Then C is pushed and then E is pushed. Then E is popped out, printed, no children for E further. Then it will move to the stack position again. C is popped out and C is printed. By this time, no children are there for C further also. Stack is empty because now the pointer is null as well as the stack is empty. This third condition gets satisfied and it will return. That means completed. When the stack is empty, we are stopping. Null pointer is also null and the stack is also empty. Both are means no further elements they can be traversed to be traversed. So we can stop. So what is the order we got? KG, DL, H, M, BA, EC. Same order we got, which was discussed in the earlier slide actually. So by using this, what is difference we observed? Here we are using an additional memory stack. And if we are converting into a program, we need to keep track of the stack position as well as the stack operations also. That means explicitly we are using an auxiliary memory space stack by ourselves. If it is a recursive, implicitly it will use it actually. So similarly for non-recursive procedure, for pre-order we will consider. Pre-order means here first root, then left side subtree, then write subtree. Here also we are using stack, print the root and push the stack and go to the root is equal to root of left till it's null. Same process. But remember how we are doing here. Our second one is same. But if root is null and stack is empty, then return. Third one is also same. Else, pop the top node from the stack and set it as a root pop node. Go to right, then step. So where we are processing actually, whenever we are accessing an element itself, we are printing. The root itself is a root node. So that's why we are printing and we are updating the root. So this print statement is before here within the else part. But here the print statement is in the beginning, at the beginning only. At the beginning means we are processing the root, then we are moving or processing the left subtree, then we are processing the right subtree. So the elements of the left subtree and right subtree are going to be processed further by popping from our, pushing and popping our, using our auxiliary data structure stack actually. So this is an algorithm, pre-order we are using. So stack, vertex is root, same we are using. First we are printing, then we are updating our right sun is not equal to 0, we are pushing. If left sun is not equal to 0, we are pushing. Otherwise, we are popping the element and making it as a vertex. That means we are pushing left subtree as well as right subtree one by one if it is not equal to 0. So this is the algorithm or pseudocode we discussed earlier, that only we will follow by using this pseudocode steps. What is the status of our stack and vertex and output? That means by tracing this pseudocode or algorithm. So what is the first root value? Root value is A and A has to be processed, that is A is printed. Then A is updated, it is not equivalent to empty. So that's why A is updated with its left subchild B. Then B is printed. B is updated with its left child D. D is printed. And D is updated with its left child G. G is printed. G is updated with its left child K. K is printed. K is updated with the left child, which is a null. So if it comes null, it will go to the next statement, third statement. Up to this is in the 2 only. We are printing and updating. Second step only we are doing actually. So third, stack is empty. Now we are going to consider the pointer is empty. Every time we are checking left child as well as right child. If right child is there, we are pushing. If the left child is, we are printing them. Right? So every time A is having a right child, pushed. Left child is printed. Again D is having a right child H was pushed. For the remaining G and A, K, no right child are there, we didn't push. So what we are doing, if any left child is there, we are printing and updating our root with its left child. Any right child occurs, we are pushing into stack. Then what we have to do, we have to pop out from our stack, that is H is popped out. From H again we are trying to move to the leftmost part. So H is printed, updated with L, right? So H is having M as a right child, M is pushed and L is also printed. Left child of L is null, it will stop again, second process it will come out of this. So what is null? Pop out. While popping, M is popped out. M is going to be made as a root and M is printed. Left of M is null, no right, so it will stop. So again, it will be popped the next element because the pointer is null. C is the pointer I was pointing now. So C is having left child E. E is going to be printed. C is printed first, then its left child is printed. And C doesn't have right child to add to the stack. When we come over here, it becomes null. So that's why pointer is null as well as no further elements are there in the stack to process. Then we will stop. So what is the order we are getting? A, B, D, G, K. So A, B, D, G, K, H, L, M, C. Same order as we have done manually in the previous slide. So that means here we have been discussing here how to use our pre-order just by using stack. So what is the logic? We are pre-order means first we have to process the root. So that's why we are printing that particular root and we are updating with its left of the root. If any right of the root occurs, we are pushing into stack. This process is continued till the pointer or a root reaches null value. If it reaches null value, then we will pop out from our stack and we will again start doing that subtree same way. This process is continued as long as our root is not equal to null as well as the stack is non-empty. If both are not satisfied, that means the stack is empty and the root is equal to null, then we will stop actually. So as the process which we are adopting here, it is using a stack again. Explicitly we need to do this process. The next one is post-order, non-recursive technique for post-order. Post-order means the element is going to be processed after left subtree and after right subtree. So what we have to do, first we have to push the root into the stack, and stack is non-empty. We have to do pop out the node from the stack and push it into the two stacks we are going to use here. Another stack, push the left and right children nodes of the pop node into stack 1. So pop out all nodes from the stack 2 and print it actually. We are going to use two stacks here. So we are going to use the push. Stack 1 is equal to 0. What is considered as a root? If vertex is not equal to null, push the vertex into stack. If the right sum of vertex is not equal to null, push the vertex as, instead of using two stacks, I can use a single stack by using negation value of the vertex. So we are assuming here, the right child is going to be represented by negative value, and we are assuming that each node is having only positive values. Otherwise, we have to use a simple other logic to avoid the processing of the another stack operation. So we are, if it is right, we are entering or pushing with a negative sign actually. So if right sign of vertex is not equal to 0, we are pushing negative of the vertex onto stack. Vertex is equal to left of vertex, we are updating. So this process is continued till the vertex is not equal to 0, means till the vertex, when it reaches vertex is equal to null, means that path is ended. Then we are popping from the stack. So while popping, what type of elements will get? Either positive or negative. Positive means left child, negative means right child. So if the vertex is, while all positive values which we are going to get are already left children, no, first we have to process left, so we will print them. Whenever a right occurs, then we have to take care of again processing the left, then we are good. So that's why while vertex is greater than 0, print the vertex node and pop from the stack, make it as a vertex. This process is continued as long as the vertices are all positive. Positive means all left nodes are there. Left nodes processing means left subtree processing first. Post order, no, that's why. Then we have to process right. So if the vertex is less than 0, we are making vertex as a negative of vertex means positive we are making. We are moving top and same process is continued. So this way we are processing here. So if you observe the same example, root 1 stack we are pushing, and while stack 1 is non-empty, we are considering here only one stack with negative symbols. I told you algorithm, we made it as a simple algorithm. So first we are pushing, keeping on pushing. Right child, if it is right child, we are pushing as a negative. If it is right child, left child, we are pushing as it is, as we are going to reach a null point. So we'll get A, we are pushing. B is a left child, we are pushing as it is. And for A, right child we are making. Right child is minus C is C pushed. Then we are checking left. We are updating with the left pointer B. Then B is pushed. B doesn't have any right children. Then it will update with D. D has a right child H. So minus H is pushed. Then it is updated with the D. Similarly, G is pushed. K is pushed. K is popped. G is popped. D is popped. So when we are popping, K is positive, G is positive, and when H comes, it is negative. So when it is negative, we are making it as a positive, and we will do the same process. So for H, again L is there, L is pushed, right? First H is pushed, then L is pushed, then minus M is there. So that's why we are going to, as H is pushed, minus M, L is popped out. So L is popped out, L is printed, M is negative again. We are right child should make it as a positive and pushed. So we are going to make it as a plus M, and M is pushed here. Then we are getting the respective values. So M is popped and H is popped, D is popped, B is popped. Up to that they are popped and printed. When we get C is negative, that is the right child. Again the process has to be started. So C made it as a positive, it is pushed, moved it to the left child, E updated, it is pushed, no right child, and it will pop from stack. E is popped, C is popped, A is popped in the same order. So stack become empty, already pointer is null, so that's why both are satisfied. So we will stop the process here. The order is KG, L, M, H, D, B, E, C, A. Same which we got manually in the previous slides. That means here we are using, instead of using these two stacks, we are following this algorithm for tracing that one, because it will become a little bit easier while implementation also. Such a way we can traverse our elements of or nodes of a tree by using these three techniques. These techniques can be implemented by using either recursive procedures or non-recursive procedures. Both of them are having its own advantages and disadvantages. So coming to the space complexity, auxiliary space, if we don't consider the size of the stack for function calls, then order of 1, otherwise the order of H, where H is the height of the subtree. But in both cases, generally we will think that recursive procedures are taking more space because it uses stack internally. Right, a little bit complexity is there while executing the process, but even the non-recursive procedure we are using, but we are using our stacks explicitly. In both cases, space is required, additional space is required as a stack, depending upon the height of the tree actually. For all recursive and non-recursive procedures, the time complexity will be order of n if the tree is going to be skewed, otherwise the order of log n. That is, the best time complexity is log n and worst time complexity is big O of n actually. Why? Why? Because we are traversing a tree. If the tree is balanced, for example, if you are going to consider the height of the tree is log n. Binary tree means log n to the base 2. So that's why we are traversing means at the most we are traversing the height of the tree only, no? So that's why the time complexity to traverse our trees, in any case, either any order of the traversal or by using a recursive function or a non-recursive function, the time taken to traverse a tree is same as your height of the tree. So what is the height of the tree? Log n. So log n to the base 2 is a binary tree. But there is an exceptional case, worst case. This is the best as well as the average cases we can consider. But what is the worst case? A tree may be a skew tree. Skew means the tree can be either traverse only left side only, or tree is generated only having right children. So if n children are there, what is the height here? Again, log n means n only number of elements have to be traversed in only in one direction only. So the height of the tree becomes as almost n. So for this skew trees, the time complexity will be order of n, and for balanced trees or average balanced trees are going to be order of log n. So that's why the tree traversal techniques time complexity will be for best and average cases order of log n, and worst case it will be almost order of n. Worst case occurs if the trees are skew trees actually. As we discussed earlier, space complexity will be almost the same in both cases, recursive and non-recursive procedures. The difference is we are going to use explicit stack in case of non-recursive, implicit stack in case of recursive procedures. In both cases, all these stack operations are constant time complexity. So that's why under this time complexity, we need not consider it, but space is required, additional space. So like that, we can traverse our trees effectively For any applications where the data is going to be stored in the form of trees, these traversal techniques can be used. Specifically for programming languages, we are going to generate compiler designs, etc. Trees is going to be various types of trees are going to be represented. Keywords are represented. Syntax of sentences are represented using trees. If you aware of the traversal techniques effectively, the respective trees can be traversed by using any of these three techniques. Thanks for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.